Alrighty, so now we're on to example 12. An archtop window is being built whose bottom is a rectangle and the top is a semicircle. If there are 12 meters of framing materials, what is the width of the window that lets in the most light? The width, we only need to have the width, and it needs to let in the most light. So you need to think about, how are you going to get the most light? Well, you're going to need a big window, right? You're going to need a lot of glass, not much framing, okay? So, well, I guess we've got 12 meters of framing regardless. So like with the 12 meters that we have to work with, what is the biggest window that we could enclose? So you're gonna need to maximize a geometry formula that is gonna allow for the biggest amount of two-dimensional space, right? The biggest amount of glass that we could make this window out of. So we're going to maximize area. So this window is made up of area of the window is made up of the area of a rectangle plus the area of a semicircle. Okay, and so you're trying to maximize the area of the window, let in the most light. Okay, so area of a rectangle, we need to start putting some variables on here, right? So we have area of a rectangle, we have area of a semicircle. Now the semicircle formula is a little bit more involved than the area of the rectangle, right? Because we know area of a rectangle is just like length times width. Semicircle is a little bit more going on there. So I'm going to start with the semicircle and then go from there. So if this is the center, like this would be the semicircle, okay? We're going to ignore all these like little pieces in between, okay? Because technically that shouldn't be there. This should be all solid glass, technically. So this is the center of the top that's a semicircle. So from the center out, that's going to be R, right? So if it was an entire circle, the area of that would be pi r squared, but it's only a semicircle. So this is going to be pi r squared divided by 2. I'll make that a capital R so that it looks the same as my other R. Okay, so now this is why I wanted to start with the semicircle, because I want to use that R to help me find the area of the rectangle. All right, so the rectangle is the bottom part down here. Now, we don't know that this is going to be a square. In fact, it probably won't be a square, okay? So we just know that it is some rectangular shape. And so if this from here over is R, then from here over is also R. And this dimension right here, we don't know. We don't know what that is. So if you just want to call that H, you can. Okay. So the area of this rectangular part of the window would be 2R times H. 2RH. And that is going to equal the area of all the glass in the window. We need to maximize this, so we want to take the derivative of this equation. Well, we're in two unknowns. So we need to figure out something that's going to help us to use substitution so that we can get this in terms of one variable. And that's where this 12 meters comes in. You have 12 meters of framing. Now framing goes around the outside. So that means that all of this plus this plus this plus the round part all has to add up to 12. So we have h plus this distance is the same as this distance. Once again, we are going to, well, actually, I guess I should think, I drew it on the outside, but I should probably be like talking about this piece in here. I apologize, you guys. So this would be this plus this plus this plus this, not around the very outside, because of course, if there's some thickness to it, it's going to change those dimensions. So just, we're really talking about that. So h plus 2r plus another h plus, now we have to go around the semicircle. So all the way around the circle would be the circumference, which is 2 pi r. But we're only going halfway around. So that would be 2 pi r divided by 2, which would just be pi r. Okay, now that has to add up to 12. So you're going to combine like terms as much as possible. So we have 2h plus 2r plus pi r equals 12. And now you can solve this for whatever variable you want to. I think I'm going to solve this for h. We'll see how that works out. If you already tried this one and you solved for r, go for it. Either one's going to be fine. So let's solve for h. Let's see, this will be 2h equals 12 minus 2r minus pi r, and then divide all of this by 2. So h equals 6 minus r minus pi r over 2, like that. I hope I don't regret my decision, but we'll go with it either way. All right, so a equals 2r. Now you're going to take all this, put it in here for this h. So this will be 6 minus r minus pi r over 2 plus pi r squared over 2. We have everything in terms of r. This r right here I should have made the same way so that it looks the same. There you go. So this is going to be 6 times 2, 12r minus 2r squared. And then this is going to be, these 2's are going to go. So this will be minus pi r squared plus pi r squared over 2, like that. Okay, so keep combining. Haven't taken a derivative yet. Let's see, this will be 2 over 2. So negative 2 pi r squared over 2 plus pi r squared over 2 is going to be negative 1 pi r squared over 2 minus 2r squared plus 12r. Yeah, that's lovely. So now take the derivative. Maybe we could have taken a derivative a really long time ago and saved us all that misery, but that's okay. All right, so power rule. Bring the 2 in the front. This will be negative 2 over 2, which is going to go away. This will be negative pi r. Here, minus 4r plus 12. Set this equal to 0. I'm just going to put my 0 over here and get r by itself. So you can subtract 12, so negative pi r minus 4r equals negative 12. Factor out r. This will be negative pi minus 4. Divide. R equals negative 12 over negative pi minus 4. Okay. And then I'm going to use my calculator to get an approximation for that. Remember, we only need to find the width for this problem. So negative 12 divided by negative pi minus 4. Looks like I get roughly 1.680. Okay, and that's going to be meters. Now that's just the radius. If we want the width of the window, that is all the way across. So that would be radius times 2. So if we multiply this times 2, we actually solve the problem, and the width is going to be roughly 3.361 meters. Okay, and that's how you do example 12. Example number 13, find an equation in general form for the tangent line. I'm okay if we write this in Taylor form because it's actually more common to use Taylor form. Either one, okay? For the tangent line to the graph of f of x equals 2/3 minus 2x minus x squared minus 1/3 x cubed, having maximum slope. So the maximum slope, if you are trying to maximize slope, we need to take the derivative of the slope formula, okay? Or the derivative of, well, yeah, the slope of f of x, okay? And then write the tangent line. All right, so you have this equation right here. So this is some curve. At some point on this curve, you are going to have the steepest slope, the maximum slope, okay? This is a cubic, so it's an odd function. It's not necessarily like symmetric to the origin. I shouldn't have said that, but like it has an odd degree. So the end behavior is going to be like down on one side and up on the other side to the infinities. So kind of have that S shape. At some point, it is going to have a very steep slope, maybe more than one spot, okay? So when we take the derivative of this, that represents the slope of the tangent lines at any point on that curve. If I want to find the maximum of all of those slopes, I have to take the derivative again. So we're actually going to be taking the derivative twice for this one and setting the second derivative equal to 0 to find the maximum slope, okay? And then from there, we'll get an x value and we'll be able to plug that into the original and get a y value, and writing the tangent line will be a piece of cake by then. Okay, so first derivative. This represents the slope in general. So that will be, let's see, -2 minus 2x minus x squared. The second derivative, now this is what we're doing. The derivative of the slope with respect to x, that would be the second derivative. And that's how we're going to maximize the slope. And that's just going to be -2 minus 2x. So to maximize that, to find the maximum, we're going to set that equal to 0. -2 minus 2x, solve for x. So 2 equals -2x, x equals -1. So at x equals -1, this curve is going to have a maximum slope, okay? So let's go ahead and plug -1 back into f of x to find what that y value would be, so we know the coordinates of the point where that maximum slope occurs. So this would be f of -1, 2/3 minus 2 times -1 minus -1 squared minus 1/3 times -1 cubed. Let's see how much we can do this mentally. So 2/3 plus 2, let's see, -1 negative, negative, plus a third. So I know 2/3 plus a third is 1. 1 minus 1 is 0, so it looks like this is going to be 2. That wasn't too bad. So the point is going to be at 1, 2. Okay, because we need that. We need this x1, y1 for our tangent line formula, our tangent line equation, I should say. Remember Taylor form, y equals m times x minus x1 plus y1. So we could put the 1 and the 2 in there right now. The thing that we're missing is m. Well, m represents the slope of the tangent line, which is not the second derivative, that is going to be the first derivative. So the first derivative actually gives you what that slope actually is, like what that maximum slope actually ends up being. How steep is this little spot going to be? So you take the x equals -1 and you plug it back into your first derivative. And that's going to crank out a slope for you. So this would be, so f prime of -1 is -2 minus 2 times -1 minus -1 squared. So this will be -2 plus 2 minus 1. So that goes, and that maximum slope is actually -1. So this represents your m, and that goes right there. Okay, we went through that kind of fast, so if you need to go back and just rewatch this or pause it in a couple of spots, that's example 13.